So, welcome everybody today. We're live, and this is the first Open World Lifelong Learning lecture, which is on continual machine learning, and it's sponsored in a collaboration between Continual AI and Hessian AI, and I'm really happy that we can offer this 13-week course for all of you publicly. So, you can participate in the course through YouTube, which many of you are already doing. The YouTube link is on the slide here again. The course materials are on the website, which is also on this slide, where you can just download the PDF if you want to zip through it. I'll be making this course fairly interactive, so I'll be asking a lot of questions, and you have multiple possibility to respond to these questions. You can either join in the Teams and just respond there. You can use the chat. Now, the people on YouTube can also use the live chat. Just as a small reminder, the YouTube has a small delay of 30 seconds. So I'll pause sometimes to wait until people can have the possibility to ask questions on YouTube. And with that, let me just dive in right into what's going to be the course outline with this week's introduction and motivation. So first of all, some rather boring bits, but just so you're aware of it, there are fairly little course requirements for this course. So I assume that there's going to be some basic understanding of the ideas behind machine learning or artificial intelligence in general, or maybe deep learning. But what this means is that in-depth knowledge of algorithms is essentially beneficial, but not a requirement. So we'll be revisiting most of the important concepts when necessary. So in that sense, you'll just have a little bit of an advantage if you already know algorithms. There is no practical tutorial. There are unfortunately no exercises for this course yet, which will be something that may be offered in the future. So programming experience is not a requirement. With respect to materials, it's going to be mainly this lecture that you're attending right now. So it's slides plus the linked materials on the slides. Again, potentially helpful, there exists a book called Lifelong Machine Learning, which has some elements of this course. However, it is a fairly short book, only 100 pages around. So it's again, maybe giving you a little bit more of an outline of what we are going to go into in more depth. And this is primarily because the field of continual learning or lifelong learning in general is rapidly evolving right now, and the step of consolidating the works, I would say, is largely still open. So I expect there'll be more books in the future. So with that, let's start right into the course. And as I've said, I'm trying to make this as interactive as possible so that it's not just the boring me telling you about things. And I'm going to start with a fairly simple question of what do you think machine learning is? So like I said, you now have the possibility to answer in chat or answer in person or use the YouTube live chat. Just maybe someone in Teams can start and just chat, put something in chat, because the YouTube has a small delay. So it's so we don't have to just have a pause. Okay, so some of you are going to say something like machine learning is about learning from experiences, or machine learning is about learning from data, or machine learning is about optimizing the performance of some specific task by learning parameters of some models. These kind of responses that you would maybe have in a textbook. And so let's just take someone just said we let the computer generate the program, which is fairly similar to this, or computers learn how to do things. So all of these, I guess, are correct answers, but also hopefully we're going to discover today that the answer to this is not nearly as simple as we maybe think it is. And for this purpose, we're going to start by looking at some definitions of what people consider machine learning, just to then go around and tell you why maybe the machine learning world is more complicated than we would like it to be. So one of the most, let's say, generic definitions of machine learning from Mitchell, the machine learning book from the 1990s, is a computer program is set to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. So it's a little bit what people just said. We basically let the computer learn how to do things, learn how to get some performance measure, solve some task with experience. But also you may have some, let's say, more in-depth definitions, which the majority of you is likely familiar with. This one is from pattern recognition and machine learning from Bishop. Again, a slightly older example, but still very relevant today. And I'm just going to read it out again, quite specifically for the purpose of introducing the idea of training, validation, and test data. So reading out the quote, the result of running the machine learning algorithm can be expressed as a function. The precise form of the function is determined during the training phase, also known as the learning phase, on the basis of the training data. Once the model is trained, it can then determine the identity of new images, which are set to comprise a test set. The ability to categorize correctly new examples that differ from those used for training is known as generalization. Now, of course, it says images here, but that's just because on the introduction page of this book, it has an image example, and you can replace images with any sort of data. But the central idea is that there's a training phase or a so-called learning phase on the basis of training data. And then there's a dedicated test set, which you have not touched to learn parameters, where you can measure generalization. And so the typical picture you'll see in machine learning books and all machine learning courses and machine learning blogs, etc., is something like this, where this is an example of a regression where you try to essentially fit a curve. So what you see here is an example of an error function that is in this case the mean squared error, I believe, which we're going to see on the next slide, that just measures how far your prediction is off from some ground truth example. So how close are you to the solution? And of course, what you'll then see in the machine learning books is this entire idea of under versus overfitting. So let's say on this example on the very left, you assume an order polynomial of 0, which is the red line. Then this will underfit in the sense of it cannot capture the complexity of the original green curve if it sees the blue data points. And this is because essentially the model does not have enough complexity. Now we can increase this to m equal to 1, for example, and then you'll get a line, and then you can increase this to m equal to 3, and maybe you'll get something that's fairly close to the solution that you want. But at some point when you go overboard, and let's say you have m equal to 9 in this scenario, you'll get into this idea of overfitting. So meaning you'll capture all the noise that is in the data, and you'll create something that's too complex. So you'll just overfit in that sense. And this is the idea that a lot of machine learning revolves around, that a lot of literature revolves around, where we try to assess this generalization and try to not overfit, right? So in the end, what we'll end up, which is as a summary of our very short sort of machine learning recap, is we'll end up with this picture where we have an error in this diagram on the left axis that we want to decrease, but ideally we want to decrease it for the training data, so the learning phase, in a way that we generalize to the test data. So in this scenario, we can see that after a certain degree of m on the x-axis, the red curve, the test set, shoots up again. So we overfit. We memorize the training data, we tune to all the noise, and we don't really capture the actual task anymore. Now, of course, this picture actually still persists, and it's very relevant even today. So it's not just about machine learning from 2006 or 1997, like I've said on the previous slides. If you look into, for example, the deep learning book, which is more recent, you'll find precisely the same picture. So you'll have this idea of there's an optimal capacity that is right at the sweet spot between the underfitting zone, where your training error is small, but your generalization error, your test error is also very small. And after this, you'll get into this idea of overfitting, where although your training error decreases, your generalization error just increases. Now, this lecture is called Open World Lifelong Learning, right? So it's about continual learning and the world being open, which I'll explain in a second. But before I do that, let me maybe ask the other way around. Now that we've seen a couple of definitions of machine learning and a couple of people saying what they think the definition of machine learning is, what do you think the goals of machine learning are? And so again, I'll just start with one example while people have the time to chat. Maybe from the previous definitions, the most obvious goal is going to be to keep this generalization gap as small as possible, right? So keep the training error low and the test error low as well. Now, rather obviously, maybe we need to then ask ourselves, is this reflective of the actual goal we want to solve? Like if we think of tasks, for example, a classification task, does this really tell us about what we want in the end? Maybe if we formulate the loss as a classification accuracy, then the picture is a little bit different already, but even that maybe is not the entire picture. So someone's correctly now saying that what we want to actually have is we want to increase the knowledge of a machine learner. And then the question, of course, is the knowledge increase of the machine learner really expressed through training loss and test loss or test errors? Someone's rightfully now saying progressing with experience or learning from experience. And this is what this lecture is going to be about, right? But just again, just to complete the circle, I'm going to give you the textbook sort of definition. And this textbook definition is, of course, when we use a machine learning algorithm, we do not fix the parameters ahead of time and then sample both data sets. But what we actually do is we sample the training set, then use it to choose the parameters to reduce the training set error, and then sample the test set. So what the deep learning book actually tells you quite precisely for the factors that are the goals of machine learning basically is, one, make the training error small, and two, make the gap between training and test error small. So it's really centered around this idea that we have a training phase and a test phase, and we can split this and we can find the parameters on the training set. And then in the end, we can have something that's sort of related to the task, but we haven't seen, which we can test on. And this will tell us precisely how we will, how good we will do in practice, right? So coming back to this overfitting picture, if we put this together with the sort of capacity idea, what we can have is we can have some sort of a plot where we have a data size that is suitable to a specific problem. So like how much data do you require versus how complex a model do you actually need. And you could do something like this curve that's shown on this slide, where the sort of the more data you get, the more complexity maybe for specific tasks you'll need in your model. But at some point it also saturates because you've just captured the entire distribution of possibilities in your training data, and your model maybe cannot capture everything as well. Now on the flip side then, this means that models are one part, but data sets are then the other. So let's just assume for a second, before we dive into the idea of continual learning and lifelong learning, that we stick to this idea of training and test sets. So we say for now that this goal as formulated of predicting on this test set as much as good as possible while minimizing this training error, so reducing this gap is really our ideal goal. And now we then need to figure out how should we acquire data sets. So how do you think, what's a good idea to capture a data set? So someone gives you a task, and then asks you basically to solve this with machine learning. Again, let's for an instant assume that this task is actually suitable to machine learning in the first place. But given that, you're now tasked to acquire a data set. How would you do this? How would you go about acquiring a data set? What do you think are the elements that are important in a data set? So something we've just seen on the previous slide that is arguably one important aspect, or could be one important aspect, is dataset size. So dataset size plays one important role in the sense of we want to capture the distribution of possibilities that we can encounter in practice, right? So the more diverse in that sense our training dataset gets, the more we hypothesize that we'll have a small generalization gap because we're capturing all the experiences, all the knowledge of our task that we can encounter in the real world. And so in that sense, what we could do is we could just try to build an as large as possible data set and try to somehow maximize diversity. The question then, of course, is, right, and someone in the chat said variance of the data. The question then, of course, is how do you know how data varies? Maybe for some parts, this is quite easy if you maybe have tabular data or so on. But even if we just think of images, the space of natural images is quite large. So if I tell you to go out and capture a very diverse data set for autonomous driving, then it's a question of how you would do that, because it's not just about sort of the different cars that exist, the different streets, different countries, but it's also about different lighting conditions, different cameras you can have. So the basically the space of possibility explodes quite rapidly. And then you essentially, or what people have done essentially, is there are two options to go about this. The first one is, and this is maybe a little bit more of a traditional way, is we capture a static training set in a very controlled way. So arguably, this may only be possible on a smaller scale, but to give you one illustration of how this is done, is you can make a protocol of things you would like to consider, as done in this texture database example, where on the right hand side you can see several images of a piece of bread, where the angle of the bread has been controlled rather explicitly, which is in the left hand table is indicated as pose. So it's either rotated 22.5 degrees to the right or to the left, or it's planar frontal. Or the same has been done with the illumination direction. So in that sense, if you have this during the trainings, in the training phase, in the training data set, you would expect that if these conditions now appear in the test, that you would be able to actually predict adequately. So one idea would be to try to list the number of factors that go into your problem, and then try to create a data set that covers this quite nicely. Now, of course, for this specific texture recognition problem, it may be feasible, but as we all know, and as I've just said, for real-world large-scale data set, it becomes increasingly complicated. So again, on the example of images, more modern data sets have taken a slightly different approach. So they still have this idea in mind, and this is an example of the very popular ImageNet dataset, which has been around for more than 10 years now, and it's been subject to various challenges and quite heavily cited and used in the literature. The idea again is to somehow have different object scales, number of instances, image clutter, deformability, amount of texture, and so on. The only question then is how to assure this, and what people are very sort of fond of nowadays is the trying to ensure this diversity through a acquisition process that just captures the real world, in the sense of, for example, that you query from social media. In this case, it was the Flickr platform. I'm not sure if that actually still exists, but it's something similar to Instagram and so on, where people could upload their videos and tag them and so on. And so the ImageNet creation has essentially queried this platform quite heavily for a lot of images, and then had a curation and annotation process with humans involved to assign labels and process a little bit. And then quite interestingly, what has then been done is a data set has been created, the ImageNet dataset, which consists of 1,000 classes, a very large number of image instances, over 1 million, and this has been divided into sort of training images, so a trained data set, a validation set, which is used to tune the hyperparameters of algorithms like learning rates, and a test set again. And so what for the last 10 years, people have very often reported is how machine learning has progressed on ImageNet, based on training on the training examples and then reporting on the test data. So what do you think? Do you think this is arguably meaningful, but do you think this should be our primary goal, to construct such benchmarks and tune sort of the performance on these benchmarks? Saying that ImageNet is so large, over 1 million images, that if we can classify all of these 1,000 choices across over 1 million images, we can say that we are constructing a good classifier for natural world images. Do you think this should be our primary goal? And if not, maybe you can also say what alternative goals you could have in terms of measuring differently or constructing the dataset differently. So someone's already said in the chat to consider data drift, whatever that means. We may get to this in a second, meaning that not all the data is static, right? So the images we may capture in this training data set of ImageNet, some of these concepts, they may change over time. Maybe for animals, ImageNet contains a lot of animals, I think over 200 classes. This is not so much the case, but certainly some of the concepts, let's say laptops, it's quite interesting that measuring the concept of a laptop according to a static snapshot of images at a certain point in time may be very unreflective of what laptops look like 5 years later. So they'll arguably still be in a similar shape or so on, but we all know how design has changed over time. So if we consider a very old laptop and then compare it maybe to a modern day MacBook, they look quite differently, apart from the fact that they are largely rectangular boxes still. Right. And so, like I've said, a very big emphasis has actually indeed been on solving these benchmarks. So one of the prominent figures that can be shown for this is this idea of top one accuracy. So how basically for every instance you classify and you figure out if the top one choice for a class is correct or not. So do you classify it correctly or not? Versus the number of operations in this diagram and the number of parameters. And as you can see, the trend is actually that the top one accuracy is rising quite rapidly. So we are essentially solving or beginning to solve this classification task on ImageNet, while our models, our machine learning models, tend to, in a sense, get bigger and more complex and more computationally heavy over time. And maybe it becomes a little bit more obvious when we look at this plot, which is a little bit more recent from 2020, where we can see the amount of parameters versus the year on the axis. And here we can quite funnily see this is not just classification models, but this is also generative models that can generate text or generate images. You may have seen the recent DALL-E just now. And interestingly here, what happens is the number of parameters here in a log scale, so it's quite an insane increase. It continues growing and growing and growing. So our models are becoming more complex. Funny enough, however, if you compare this to datasets, maybe this is not so much the case for datasets, with a little bit small of a star about the recent years, which we'll see on the next slide. But for a very long time, at least in the early 2010s to late 2010s, the model size has grown quite a lot. The GPU power we've put in has grown quite a lot, but the dataset size, for example, for image classification, has stayed roughly constant, or there hasn't been too much of a move in terms of dataset evolution. Now, of course, I may be simplifying this a little bit, and someone will rightfully now tell me that datasets have indeed developed. This is true, actually. Very importantly, there has been quite a lot of other developments that are not just about dataset size. So importantly to highlight for the ImageNet, for example, researchers have indeed gone back to ImageNet, for example, and have excluded various images with respect to fairness and representation of humans, racial slurs, etc., from the dataset. So there's been a different sort of progression in terms of dataset. But size is maybe not the thing where you see a paper appear every week or so on datasets being changed, in contrast to almost a new model or a larger model appearing every week now on archive or other platforms. So what you typically see is you'll see the models increase. Just to give you one example that indeed now there's also a push of growing dataset size. There are datasets like JFT, 300 million or 3 billion, where you can see that on ImageNet again, the accuracy, sort of the error rate, decreases even more if you also grow the dataset size, in addition to growing the compute on the x-axis here. Unfortunately, a lot of these datasets are not public, so I'm not sure if the JFT dataset is public now, but it has not been public for a while. Similar, there's every time a new transformer model comes out, there's a question of, is there going to be a trained version of it? Is the dataset going to be available? Most of the time it is not, until there has been a lot of effort and pushback until this happens. But in any way, there's this idea somehow that there's a model centrism. So a lot of developments that just try to push algorithms, push models on existing data sets, and maybe some community that pushes a data centrism. So they assume that given a specific model, like a vision transformer in this case, or a natural language transformer, we can grow data sets to make these models just learn more about the world. So in summary of the start of the recap of machine learning, I think the picture that most people are really familiar with in machine learning is the following, and this is taken from a blog. You'll find various versions of this all around the internet, including in machine learning textbooks. And the idea is really this chain of things that you have to do in order to create a machine learning system. And it's almost like a waterfall. So you start by defining an objective, and then for this objective, you collect some data. Now, this data, it may be useful, it may partially not be useful. So you prepare the data in some way, maybe you clean it, maybe you blend it, maybe, as someone just said in the chat, you use some synthetic data to augment your data set. And you can eventually label it if that's sort of your desired task, includes supervision. And then once you have this data set, you do this train, test, validation split, and you start selecting algorithms. So you make a choice of what type of model, what type of machine learning model would you like to have on this task, what specific parameters, hyperparameters do you need for this model, what learning algorithm, etc. And then you start training this model. Now, while you train this model, you do cross-validation to pick these hyperparameters and eventually try to get the best model you can. So you can then test it on some held out data to assess generalization. And if it's an actual real application, you deploy it into some sort of web service or so. And so the question that we're going to ask ourselves in this lecture is going to be, but what if we want to continue learning tasks? What if we start, for example, in this robotics example, where we have a robot arm grasp a box as a first task, but then maybe after we've learned how to grasp a box, in the next task, we want to learn how to also put that box into, a cube into a different box. So how do we now place it somewhere else, this object? And maybe then we can also figure out how do we package this this box? How do we enclose it? How do we wrap it so that it can be shipped? Maybe also at some point we receive some deliveries or so we want to open it again. Maybe we want to stack the boxes. So the number of tasks that we can imagine, they can naturally grow over time. And it's maybe a little bit of a question whether creating a sort of a weak learner, a weak machine learning system that's very specific to every single task is the thing we ultimately want, or whether we eventually want to create this machine learning system that continues to learn multiple tasks over time. As an alternative to the exact same thing, if you stick to this image classification example, just because it's a popular one, we could also think that even if sort of our training set is quite good for a specific category, we could also think of the number of categories that we can have, because categories are essentially also a human concept. They can always be distinguished more. So, for example, on these birds that may or may not be related, they can can either be distinguished further, or there may be new bird types because there's just a lot of species that we want to add to our model over time. Now, the big question is why, or let me put it the other way around. Can we just iterate this arrow that we've seen with the machine learning workflow that had these steps in a sequence? Can we just take that arrow and iterate it by putting it to a circle? So can we take these steps of data preparation, coding the ML model, training it, deploying it, managing the versions, checking the predictions, testing, and so on, and then just keep cycling this? Do you think that's something that's sort of going from this chain of steps? Can we just make this chain a circle? What do you think may happen if we do that? Okay, so the first thing that can happen is, and someone mentioned it earlier already, is that the data distribution may shift, right? So that if we keep on going this, at some point we're going to reach maybe the prepare data step, where the type of data we prepare is not really the same as before. And someone has actually asked, if the data drifts from the previous distribution, is this also a scenario that is considered under continual learning? We'll get to that in a second. Some people may not classify this as continual learning. In this lecture, I hope I will convince you that it is a part of continual learning in just about the next 30 or so minutes, so that we can essentially develop an understanding of continual learning that's more broad. So in my view, continual learning, or maybe more generically lifelong learning, is about the idea that we have these various elements that can change over time. And so to highlight a few, I'm just going to give you a bunch of examples to hopefully increase your understanding towards this. So let me first start with this last picture of this iteration. I'm going to show you possibly 10 or so slides of why this is a lot more difficult than we would perhaps imagine. And let me start with the human motivation for this, where someone has actually nicely done a study on humans having the small experiment where they get a cue, which is a specific environment with grass and the sunlight, and then they get a stimulus, in this case a tree, and for the tree, the leafiness, so the amount of leaves on the tree, and the branchiness, like how many branches it has, varies. And the human is tasked to provide a response of whether this type of tree should be accepted in this specific environment, or whether it's not a good fit. And so for this specific case, it turns out, maybe not surprisingly, that humans seem to actively benefit from temporal correlation during the training phase, right? So if you essentially show them the trees in some sort of order, like you progressively increase the branchiness, it's a lot easier for the humans to identify which trees should be accepted in a specific environment versus which trees should not be accepted, in contrast to completely randomizing the process, like it completely shows something else every time. Somehow, maybe this is not surprising that you can learn from this temporal correlation, but what may be surprising to one or the other is that this may not necessarily be what machine learners do. And so I was going to ask you this question, but I've almost answered it myself now. But just to do it anyway, what do you think will happen if we present sort of both of these ideas to the machine learner? So just to repeat, on the one hand, we can show a curriculum that's completely interleaved. So at every, on this example of two colors here, we have two types of examples. We show first a blue one, then an orange one, then a blue one, then an orange one, then a different orange one, and then we just alternate these all the time, versus this idea of we first show all the variations of what constitutes orange, and then we show all the variations of what constitutes blue. And so Correct. People may be familiar with this phenomenon. It's something that machine learning, a scenario where machine learning typically performs rather poorly unless you really shuffle the data. So when you shuffle the data on this top left graph here, you can see that if you measure the accuracy for both tasks, the blue and the orange one, you will get, in this scenario, quite a good solution for both of them. But if you go with this training curriculum, what will happen is the orange task is going to be, like someone just said, is going to be completely forgotten as soon as you do the task switch and continue only seeing the blue parts. And so this is quite interesting. It's a phenomenon that's referred to as, in this case, I guess, catastrophic forgetting, or just forgetting in general. And it's something that machine learning has struggled with for a while. That is one instance of challenge that is definitely not captured if we just look at these static training and test sets, right? So if you capture a static train set and then maybe even split off a test set of it, then this is something you will not encounter because it's just something you do not consider in your setup. A lot of people are actually considering this scenario nowadays, and they are referring to precisely this problem as continual learning. I think it's a very important part, but I hope that in this lecture we can open up the scope a little bit and now consider also all the other factors that go into continual learning and not just this forgetting phenomenon. And so on the next slide, I'm going to essentially tell you why do we need an entire lecture to talk about continual learning or lifelong learning. And it's this idea that it's not just about forgetting, it's also about the fact that the world is inherently open. So the world it's not just, think of a video game like an open world game. Everywhere you go, you constantly explore something new. It's not just the idea that you have these discrete task switches, but everything is continuous, and no matter where you go, things change. So the distribution itself changes even when we maybe see similar concepts, or the concepts itself change, or the tasks change, and so on. So there's various forms of changes, and we encounter all of those in the real world. So all of these become important. And so the prime example that is usually popped up when continual learning or lifelong learning is popped up on is indeed this catastrophic forgetting phenomenon. And just for completeness, putting it here again to emphasize one crucial aspect here. This phenomenon typically happens when you assume that at the point where you switch the task, you constrain your machine learning to no longer revisit the old task data. So in other words, if you do this interleaving, you can also do this interleaving by doing a little bit of revisiting sometimes. You will not necessarily have catastrophic forgetting. But if you just have like a stream of data and along the stream of data, your task changes, you will have catastrophic forgetting inevitably. And not just in deep neural networks that are modern, but also in various other machine learning algorithms. Now, if you think of why this could be the case, we'll talk about this in detail in one of the upcoming lectures. But just as a small sort of as a small inspiration, then it may be because the way we optimize machine learning models and the way we formulate this entire idea of training set and then testing and having an algorithm that's inherently greedy. For example, if you think of stochastic gradient descent, you just optimize a loss in expectation of what the current data is you see, then maybe this isn't even surprising. So in that sense, we'll need to think about how do we change our setup of machine learning to address this challenge. But this isn't the only thing that happens. So something that's also quite interesting that many people are not aware of, but it is regaining attention currently in the literature, and especially, I suppose, in industry folks who encounter this problem quite often. It's this question of what happens if you encounter something unknown. So just to give you one small example, let me ask you, what do you think will happen if you, for example, train a machine learning model? Say, just for simplicity, it is in fact a deep neural network, like a modern convolution neural network, and you train this on fashion images, and then later someone gives you an image where the only thing you have is an animal in the image. What do you think will happen? And so again, just to make the answer choices that you have concrete, maybe say you have 10 different fashion categories that your previous classifier can put out, right? It can It can say it's a t-shirt, it can say it's some sort of sweater, it can say it's a pair of trousers, um, this sort of thing, right? So right, someone's going to say it's a problem of out of distribution. So the data is out of distribution. This is correct. But do you think this any model that you have in machine learning, or most models that you have in machine learning, will handle this correctly? So what do you expect it will predict? Yes, it will predict exactly, someone saying this, it will predict one of the pre-described categories. So that's quite interesting. Now, of course, the question is then, it's rather obvious that it predicts one of the pre-described categories because it doesn't have a different choice. So as someone's saying right now, it could output everything. The question, however, is, can we figure out if this prediction that you put out is in fact different from the real prediction on an actual fashion item, right? So do you think it will be distinguishable from what the expectation would be? And so what I mean by that is, if you think of, for example, probabilities and you have 10 classes, what you would ideally want is, you, for such an out of distribution image, you would have a prediction that gives you equal chance, equal likelihood across all categories, right? So even though it's forced maybe to pick one category, maybe it picks one category with 11% versus all the others with 9 point something. And funny enough, someone's in the chat is saying, no, they will not expect that to happen, which is a good answer. It's, let's say, the more likely answer, and it's saying it could for sure be a t-shirt. This is actually, in fact, what happens in the majority of current machine learning models. And although I'm picking a classification example, that's actually something that also happens in unsupervised learning, for example, where of course then you don't pick a wrong category, but what you do there is you assign a likelihood that's essentially indistinguishable from that of your training data, meaning you think, or the model expects it to be part of the train distribution, right? Which is of course wrong. So this idea that models do not really predict robustly as soon as you move into like an open world is another challenge besides catastrophic forgetting, which is, in my opinion, rather major. And again, if you think back of where we started this lecture from today, this idea of we capture a train data set and we capture a validation data set and we capture a test data set and we measure these performances and say our goal is minimizing the training error and minimizing the generalization gap. The challenge here is that this idea on the slide of having unknowns that are encountered is inherently not captured in this way of setting up machine learning. So we somehow assume that the test and the validation, all these things we see, also belong to the same concept, the same distribution as the train data has captured from. And so the thing we have to ask ourselves then is, how do we solve this problem, essentially, which is going to be, besides catastrophic forgetting, is going to be another lecture. Now, someone may possibly very correctly intervene now, but what if we just add another class in this idea and just dump in everything that's background, right? And so in this scenario, then we can say that we just aggregate images from Flickr again, like we've done in the ImageNet, and we just put in everything that does not correspond to one of the classes that we wish to predict. And of course, that's one way maybe to do it. But let me just say that this is almost like saying we do inference with the universe, because what we would have to do for anything that's not a very constrained problem is we would have to create a background class that captures the, like in the worst case, the entire universe, right? Of course, it's not the case. So if you're maybe in a warehouse, the number of options you have are indeed quite constrained. So it could be a legitimate approach. But in general, if we really wish to go into a completely open world, like let a robot navigate outside, then this will be very challenging indeed. So just to give you a quantitative example of this, of what someone has just correctly said, is on the left, you'll see a histogram where on the y-axis, you'll see the number of images of various data sets. you'll see one of the data set has been trained on, which is our fashion example. It's in green. And then on the x-axis, what you'll see is the confidence or the probability of the output of a neural network classifier model, a convolutional neural network in this case. And now maybe after I've given this explanation, it's not so surprising to see this, but the unfortunate event is that it's very indistinguishable, right? So whatever I've just told you qualitatively is indeed also quantitatively the case, and just so you have some evidence, you can see it here. Now, what you would want in practice, of course, is you would like to have the confidence of the predictions of your trained data set, the green one, completely on the right, so 100% sure that this is the correct category, and all the other ones as close to random chance on the left as possible. This example is really unrealistic, or at least that's what someone could say, right? Like, when do we ever want to create a classifier that is supposed to capture the idea of fashion, and then later we give it random images of, I don't know what, a car or something, right? And in a sense, that's a legitimate critique, because if we think of a lot of machine learning applications, recommender systems, or your Amazon, or you really even Zalando, and you want to classify fashion, then this scenario will almost never occur, especially even if you, let's say, put up a platform where someone can upload whatever they want. You can still provide a small note and say, please, like, if you upload garbage, essentially you're going to get a garbage prediction, right? So an interesting thought experiment would be, what do you think will happen if we don't make it so extreme, but we stick to this idea of train test evaluation of static data sets, but just repeat the collection process of the data set a second time in the exact same way and evaluate again? What do you think will happen? Do you think we'll replicate our results exactly? So can we reproduce by just repeating everything? And of course, maybe that's a little bit of a trick question, because the fact that I'm asking you this question may already indicate that the answer to this is likely no. But you can just ask yourself this question and internalize a little bit of whether that matches your expectation. Because even just asking this question to yourself and trying to find an answer for it already lets you critically think about machine learning quite a bit, I think. Again, to give you a quantitative example, which I believe was one of the more interesting works in the last couple of years, someone has actually done this for ImageNet. So quite interestingly, to really go through the complexity of recapturing this data set again and walking through all the steps. But what we can see in the plot, and maybe this is in fact a little bit surprising because the example is not very extreme. We would expect that if we follow the exact procedure sort of to the detail, we would get almost the same result. But what you can see in the plot here is that for the blue sort of points and the red linear fit through it, we can see that the test accuracy on this second test data set that is supposedly the same thing as the original test set of ImageNet, you can see there's a massive drop in accuracy for this classification task. So the expectation would be that you just have this this linear curve in the dashed black version here, but you actually see a consistent degradation. So even if you recapture this entire data set in the same way again, because there are some factors that are not explicitly controlled, you will unfortunately encounter this performance drop because the distributions shift. So independently, I suppose, of whether you have this very discrete, very strong shift of moving from one category to an entire different category, or whether you're just changing the statistics of the data you've acquired within the category, you will inevitably encounter challenges with respect to the world being open, with respect to the statistics changing all the time. And to add on to this then also lets us ask, if we know about this, and we know that our statistics are changing in various situations, and maybe even concepts are changing, then we may also ask ourselves, how do we then add data over time? How do we grow our data set? So we understand now that a static data set and a static test set is not the best idea possibly. It's good to sort of compare algorithms between one another, maybe in some scenarios, or for very constrained applications where this is legitimate. But overall, let's get away a little bit from this picture. So something you can then ask yourself is, let's construct a loop around the data where the idea is that we train a model, and then after training on some data, we now have almost an unlimited pool of data available in some data streams where we can decide to query instances from, right? And this is, I think, a very realistic scenario nowadays, because in many applications and many scenarios, especially given the internet, the stream of data that we have available is massive. And processing all this data is maybe not possible right now, at least not for most institutions. So the question is, how can we, for a specific set of tasks that we have, query data instances from this data stream, from this pool of unlabeled data, and then use it to add to our data set such that we maybe get the best decrease or the best improvement in performance according to our task criteria, right? And this could be, again, if we want to just a decrease in loss, if that's what we desire. And of course, it is a question of, is that what we desire? So this is the idea of active learning. We're going to talk about just the circle again for election specific. And so for those people now already who are a little bit familiar with continual lifelong learning, at this point, you may notice that the definition that I'll use for lifelong learning is quite open. So it's really anything where this idea of static train validation test set no longer cuts it. So when we need to move away and have some elements of continuity, some concepts over time, right? Some evolution. And so we've had the catastrophic forgetting idea, which is challenging. We've had the idea of robust prediction for unknown data, which is challenging. And now we have the idea, how do we pick data next, which is challenging. Why is this challenging? Let me ask you, how would you actually intuitively pick data? So even if I give you a single task and the task does not change over time, but I'm just asking you, how can you improve the task performance by adding new data to your data set? Or how can you maybe make the prediction more robust or more widely acceptable for more scenarios by adding more data? What would be criteria by which you would select data? So one maybe obvious choice, which someone has just mentioned, and that's quite interesting, is data which were classified wrong before in the for the idea of a classifier. And this is maybe not a bad choice, right? Although we have to think about the previous question of is this classified wrongly because it actually is classified incorrectly, or is it classified incorrectly because we are encountering this open world problem where it's just an unknown concept, right? And as we've just seen, unless we solve the task from before, we cannot really distinguish these necessarily, maybe. So someone says the most representative instances may be the ones that are hard to predict. Now, so in that sense, that's a good answer in a different way, but it requires us, or we are confronted with a different challenge in trying to assess how hard, like how difficult a data instance is, right? We'll talk about this in a second. It's an interesting idea. Let me just briefly tell you what will happen if we emphasize novelty. So let's just say we emphasize novelty and say we pick the one that gets classified wrong with a very high sort of probability, right? And that's a good instance to pick next. So what do you think in my current camera stream? If my idea is maybe you want to, I don't know, construct a model that detects my emotions, for example, what do you think would be the most novel example, the one that I most surely will classify wrongly, and which will spike sort of any metric and novelty with respect to what is previously observed, because the discrepancy is just very large. What do you think this one would be? Okay, if no one's giving a response to this, I can I can just intuitively show you the I can move around a lot, right? So, and I can pop up a new, as someone said, like data, which will like with a new category. Of course, I can now put an emotion in that I have previously not shown you. Maybe I now get angry for some reason, which I shouldn't be doing in a lecture, right? But maybe I now do, and so this flags some criterion of it's very distinct. But I think most likely what would happen is my camera just goes out, so you'll get noise in the image, and this noisy image is obviously completely different from anything I've seen during training or during this live stream right now. So this will spike any sort of criterion of novelty quite heavily. The only question, of course, is then, is this data meaningful at all? Does this actually have any concept that I'm interested in, right? So even if I cover my camera like this, you will not really get anything from this because it doesn't contribute to your task. So somehow we're confronted with this idea that we want to diversify our data when we now pick new examples. We need to make sure that we are solving this unknown sort of concept problem, or maybe we want to at least figure out if it is an unknown concept so we can start representing a new category. But we also need to make sure that we don't just overemphasize novelty, because if we overemphasize novelty, and there are various cases where complete failure modes would just be captured, which we're actually not really interested in. So we query data that's completely unrepresentative of the task. Maybe more sort of constructively, let's think about, someone has mentioned this idea of hardness, of difficulty of an example. So we want to query examples that now are increasingly becoming hard. And maybe that is an interesting idea. It's actually an interesting idea, which we are again going to talk about in one of the upcoming lectures, which is commonly known as curriculum learning. So someone has done, actually Benjo has done, if you don't know him, it's a Turing awardee. Benjo and et al. Have done a very nice experiment in one of the papers where they've taken a ranking language model trained on Wikipedia, where they trained the model using a curriculum and not using a curriculum. So what this means is no curriculum means they just take the entire data set of words or vocabulary of Wikipedia, they just randomly shuffle it, they do the machine learning thing, and they monitor this training curve on the right here in the dotted red line after millions of updates of the machine learning system, right? But alternatively, maybe something that's extremely intuitive for language would be to start with the easier words, and easier in this case is described as how common is a word. So how frequently would you encounter a word, and start with those words first. So you start the training just with the 5,000 most frequent words, and then later you add the, after you've maybe converged a little bit, you start adding the 10,000, so the 5,000 next frequent words, so you're at the size of 10,000, and you proceed with this. And what then happens is, in this example, is that initially you may be performing poorly if you, of course, measure on the entirety of Wikipedia, because you're limited to a subset of 5,000 words. It doesn't really help you to predict on the entirety of the language that exists. But after a while, the machine learner in this case seems to profit quite nicely from the fact that it has first learned the easy examples, and the hardness or the difficulty of the example, according to this specific criterion, has been increased, eventually surpassing this idea of just shuffling everything and training on the shuffled data set. And this is interesting because we can also think of this in other data where maybe the concept of difficulty of an image is less clear, but we can have ideas of how we could formulate something, right? So in this example on a neural network with images, could maybe think of, if we're interested in fruit or vegetables, we can start with image examples here that don't have a lot of background, and there's a single instance in the image. And then later, as we grow harder, as we grow more complex, we add vegetables that maybe appear in with more clutter, with where there's more instances in the image. Maybe vegetables that are just whose shapes are increasingly more complex, and fruits that are just have a lot more details, like seeds and so on, and then grow our data set that way in the curriculum, right? Now, of course, then the question is, and this is going to lead us to our next challenge, which again will be a part of the lecture later, is in this image, we see a model that's now static, right? So again, we're at the point where the data changes and we grow our data set. And in fact, the model on the previous slide that we've assumed for the Wikipedia, it's a static model in the sense of that the architecture of the machine learning model doesn't change. It has a fixed number of parameters and we just assume everything fits in there. But what do you think in this picture will happen if you just continue growing your data set and you stick to the same model? So what's indicated here is that you hope what will happen is that different paths in this neural network will capture different concepts. And so you'll have like different subsets of the models being representative of different subsets of the data. And in this scenario, this may be okay because you're not going to encounter the earlier described catastrophic forgetting phenomenon, because you're not just seeing this as a first task and then the next thing as another task, but you're just growing the data set, right? So you can't forget because you're growing the data set. But of course, what you then have to ask yourself is, this first data is quite easy. It's actually just apples versus oranges on a white background. So what's a classifier that can distinguish this quite well, almost perfectly maybe? It's a very easy one. It's one where you just check, is it white background with red on top, or is it white background with orange on top? So a simple color classifier will likely do the trick in this scenario. And so if you want to express this as a neural network, you need a very small size of parameters, a small amount of parameters, and maybe a very sort of shallow neural network with just one layer to do the trick here. But then if you keep growing your data set, the capacity and the complexity of the functions you can express to this is potentially not enough. So you can no longer capture the tasks that you have, the data set complexity that you have with this machine learning model, with the number of parameters you have. So sticking just for simplicity to this specific neural network example, even if you decide to go with just neural networks, you're already going to be confronted with various questions of how to deal with this. Now, more specifically, as an example from this paper, what you could do is you could take a specific unit and split it into two. So that's one option. You could grow neurons. So basically, you could add an additional unit, add an additional set of parameters. Or maybe you could also say, yeah, sure, width in a neural network is one way to add complexity, but also the number of layers, so the depth is a different form of complexity which you could add. So maybe that's something you do. So already here, again, you're confronted with various questions ranging from, first of all, when do I need to add complexity? And then how do I add complexity? And then, of course, how do I add complexity in a way that it's befitting my task, right? I could always just make my model massive, like some models are actually doing in practice nowadays, and just over-parameterizing everything. But if we're really interested in capturing like an adequate complexity of a specific task, it gets quite challenging, especially when we then think of a continual scenario where maybe the distribution not only shifts, but the task itself shifts, because we then need to maybe ask ourselves also, is the inductive bias that we've assumed, so even maybe the choice that we have made for a specific model like a convolutional neural network, still adequate in the sense of that what if someone as a second or third task coming from images gives us tabular data, and the idea to now use a convolutional neural network is maybe no longer as sensible as defaulting to a different model option in the first place. So I hope I could give you an outline on the last slides of, first of all, what we're going to discuss a little bit in the lecture, Second of all, that there are various elements that become quite challenging, but also quite interesting and important to think about when we move away from this idea of having a static training data set and a static test data set, which just do the trick, right? So this underfitting, overfitting, generalization gap idea. So I hope I could give you a nice outline of that. But also on this slide, I would like to now emphasize, and this is going to be the scope of this lecture, right? Lifelong open world, lifelong learning. That ideally, if we think of biological systems, we hypothesize that biological systems can do all of these tricks together. So they can do all of these tricks at the same time. So on the one hand, somehow they can transfer to new tasks and adapt their existing knowledge to even learn new tasks more rapidly. They can do this without catastrophic forgetting of previous tasks, even if the task switches are quite large. They can figure out the similarities between tasks. They can learn tasks, which is also interesting when no one tells you that this is a different task, right? So it's not just about supervised learning. And ideally, we want to do this in a noise tolerant way. So what I've said before, if we do these if we add these unknown examples, then we should be able to deal with this in a resource efficient way, right? So in a sustainable way. So surely one idea would be, let's just make the largest data set possible and the largest model we can think of and currently compute. And maybe this is going to get us somewhere. And of course, it is getting us somewhere. But maybe there's an alternative way to think about machine learning. So as a summary of the course, the objectives and the content that we're going to see in the next couple of weeks, maybe as a first step, we can all realize and acknowledge that iterating the simple arrow that we've seen in the beginning of the machine learning steps, how it's frequently advocated, is not as trivial and definitely not as easy as just turning it into a cycle and just repeating the steps one after another all the time. So we've seen that on each of these steps, we'll have a very challenging question waiting for us. So for prepare the data, we'll have the question, what data should we actually have next? For coding the ML model, we should ask ourselves the question, is our ML model still the best choice? Does it need to be extended? Do we maybe even need to switch the ML model or do some sort of hybrid ML model? Do we then in training, we somehow need to account for this catastrophic forgetting challenge? And then later in the versioning, deployment, and prediction stages, we need to figure out what it actually means to have a specific model version, what it actually means to ensure that this specific model is robust, that it can indeed only predict for the tasks we're interested in and correctly identify tasks and data that is uninteresting to us, and so on. So in that sense, we will have a very broad scope, because even if you just consider the machine learning workflow as is here without the continual aspect, so just if you stay within one task and you just try to iterate this, you're already going to have a lot of questions, right? So for each of these boxes, you'll have to ask yourself, what is the correct amount of data? How redundant versus diverse is this data? How do you need to clean and pre-process it? So all these steps that already go into the static machine learning workflow. But we'll now need to also add these orange boxes in this diagram, which we'll talk about in detail in each of the following lectures, where the questions that we've just very briefly sort of outlined on the previous slides come into play, like data selection, task similarity, model extensions, etc. So the idea is, on the one hand, to broaden up the understanding of what happens when we take machine learning out into a world where various facets of our workflow can change over time. And not just the catastrophic forgetting or the model one, but also the data sides and the prediction and evaluation sides. And so that at the end of this entire course, we can have an understanding of this image, but also have an understanding of the present state of the art towards solutions of these individual elements, but also this entire circle as a whole. So as a small spoiler, at the time of doing this lecture, I don't believe there exists any, at least not a public one, approach that would do all of this in a satisfying form. So this is something that's subject to future work for sure. But what we are going to encounter is we're going to encounter various approaches that have spanned at least some of these directions together, and definitely have tackled individual dimensions quite well already. So just to give you an outline, or a very simple outline of the course, what we're going to do to make this as understandable as possible is we're going to try to understand basically this diagram here, in a sense of that we'll walk through each of these dimensions of this former plot individually. So what we're going to do is we're going to pick the machine learning parts, the niches that are called, for example, open world learning, active learning, as we've seen, but also these ideas of zero-shot, few-shot, multitask learning, domain adaptation, like what happens when the distribution changes, transfer learning, all the way down to our current understanding in the research community of continual and lifelong learning, and see how these fields have various elements of continuous learning in themselves, how they have historically developed, but then also how they interconnect, so that hopefully we can have an understanding of open world lifelong learning that somehow has these synergies between all of these elements, and provides an interface between all of these elements. And as you can see on the plot, it's a topic that's where it's like highly timed to dive into, because the number of publications, if that's one measure to assess the popularity of the topics, it's exploding quite rapidly in the last years, as is obviously all of machine learning. So with that, I'm at the end of the current first lecture, where, like I said, I hope I could give you a nice overview of what's to come in much more detail on the individual questions, on the individual aspects, and the historical overviews in the next weeks. And if you have any questions, feel free to ask them now, both in chat or in voice. No, I've mentioned this at the beginning. There will not be any exercises, programming exercises in this course as of now. There'll likely be some next year if we ever do another rendition of this course, just because, it takes a lot of time, right? So ideally, this is something we'll strive towards, but right now it's not there yet. I will try to, however, because I think this is an important part in the next lectures, where it becomes a little bit more about like practical algorithms and so on. I will try to point to both resources in terms of programming and in terms of frameworks you can consider. In fact, something that is not on this plot here, and also on this machine learning cycle on the previous slide, is that there will in fact be an entire lecture dedicated to software. So what is going to happen there is we're going to first historically walk through the role of software and software frameworks in machine learning, because these are indeed very heavily influencing how machine learning develops, and where basically what things are possible and which are also possible but less likely to happen because people there's just a higher barrier, right? And then that lecture, of course, obviously also dedicate the second half to, let's say, continual or lifelong learning software in particular. Well, thank you for the feedback. I'm also looking forward to the rest of the course. And so if there are no other questions, I will just stop the live stream now. Feel free to just ask questions next time, or you can also just stay in the Teams and ask the question once I'm no longer online, if you don't want to be recorded on YouTube. Feel free to also just join the Continual AI Slack. You can find it on the Continual AI website, where you could just ask questions asynchronously. or you can visit the either the OWL Lab website or the continual website where it links to the OWL Lab for the PDF materials, and maybe some other links I'll provide in the following weeks. There's not much to share for the first lecture now because it's basically just an introduction, but there will be more materials in the next weeks. So thank you all for joining. See you next week.